Every time you open Netflix, millions of requests instantly start flying across servers all over the world. But what actually happens between your phone, the internet, the cloud, and the back-end systems that are responding in mere milliseconds? Most developers use APIs every single day without really understanding the underlying architecture. And if you're building at scale, that's a massive blind spot. Today, we're going to break down the exact engineering mechanics that power the modern web.
Here is the blueprint for today's explainer. We'll start with client-server fundamentals, then move into HTTP and API design, dive deep into component architecture, and wrap it all up with cloud scaling.
All right, let's jump right into Section 1, Client-Server Fundamentals.
At an engineering level, the client-server architecture is literally the foundational communication model of the internet. It's pretty straightforward. A client requests a service, and a server listens, processes it, and responds. Now, unlike decentralized peer-to-peer networks, this centralized model gives us a single source of truth, and that is absolutely crucial because it makes it so much easier to update your business logic and scale the whole system securely.
Let's trace the actual data flow here. Over on the left, we've got our client. This could be a web browser, a mobile app, maybe even an IoT sensor. It fires off an explicit HTTP request across the network. Then, on the right, the server receives that raw data, runs whatever business logic it needs to, and fires a response right back. It's this endless, totally predictable loop of requesting and receiving.
But here is the cardinal rule of this centralized architecture. The client always initiates the conversation. Traditional servers don't just randomly start talking to clients out of the blue. They basically sit there, completely idle, actively listening and waiting until a client explicitly asks them for something. Now, this is different from persistent connections, which we'll actually get into in just a second.
Moving right along to Section 2, HTTP and API design.
So you type a URL into your browser and hit enter. What actually happens? A highly complex lifecycle fires off in literally milliseconds. First, the browser queries the DNS to find the IP address. The DNS returns that exact IP. Next, a TCP handshake happens to establish a secure connection. And only after all of that does the actual HTTP request go out over the wire.
You can think of DNS kind of like the internet's phone book. It maps a human-readable name to a unique IP address, which is basically a physical mailbox sitting at a provider like AWS. When your machine routes data to that mailbox, it packages it up with headers, things like content type or authorization tokens, and the server replies with status codes. We all know these. 200 means success, a 404 means the resource is lost, and a 500 means, well, the server crashed.
Now, to put things into perspective, while an IP address gets you to the building, every single machine has over 16,000 available ports. Think of them like apartment numbers. For standard HTTP traffic, the client knocks on port 80. For secure HTTPS, it knocks on 443. And when it knocks, it uses specific verbs. A GET request to read data, a POST to create it, a PUT to update, or a DELETE to get rid of it. Okay, so we're connected. Now we need a language. REST APIs use standard text-based JSON, and they are completely stateless. Now, if you need a bidirectional real-time connection, say for a chat app, you'd want to use WebSockets. But for pure ultimate backend speed, modern systems are moving to gRPC, which uses strict binary contracts and protocol buffers.
REST is fantastic for public-facing data. It easily sends JSON payloads to web browsers, and it's universally understood. But gRPC? Its compact binary serialization makes it ridiculously fast. So a massive architecture will typically use standard REST for its public web traffic, but behind the scenes, it'll rely entirely on gRPC to route millions of internal microservice calls instantly.
Let's look under the hood in Section 3, Component Architecture.
The reality is, the server is rarely just one piece of software. If you're using a thin client where the browser is just rendering data, the heavy lifting happens here on the back end. A packet hits port 443 and meets a reverse proxy, like Nginx. Nginx is blazing fast at serving static files, but for dynamic requests, it cleanly routes that traffic down to an application server, maybe running Node.js or Spring Boot, and that's where your authentication and business logic actually live. The final step in this stack is persistent storage. Your stateless application server needs to securely query user data. But listen, if 10,000 users hit the app server at once, opening 10,000 direct database connections is going to crash your entire system instantly. No way around it. Instead, we use connection pools. The app server utilizes a limited pool of persistent connections to safely query relational databases like Postgres or flexible NoSQL stores, making sure the storage tier never gets overwhelmed.
Finally, let's talk about surviving massive traffic in Section 4, cloud scaling. In the real world, you aren't managing single physical machines in a closet somewhere. Cloud providers abstract physical data centers into virtual blocks. AWS, for example, provisions EC2 instances. These are virtual servers that you can spin up or destroy in literally seconds to meet user demand. They assign dynamic IP addresses on the fly, building this massive, globally distributed backbone.
But to handle massive spikes, you need traffic cops. Enter the load balancer. An application load balancer distributes inbound requests across a horizontally scaled cluster of servers. If one server breaks, the load balancer instantly detects it through health checks and seamlessly reroutes the traffic. Notice I said horizontal scaling. Unlike vertical scaling, where you just buy a bigger, more expensive machine, horizontal scaling lets you infinitely add smaller, stateless servers to share the load.
At the absolute pinnacle of scaling, we have container orchestration. Developers package their apps into uniform Docker containers, and a Kubernetes control plane automatically replicates and heals thousands of application pods across distributed nodes based on CPU load. Alternatively, you could go entirely serverless. Architectures can use event-driven functions like AWS Lambda that auto-scale per request, though, you might have to trade off a tiny bit of cold start latency there.
Well, we've journeyed from a single browser click all the way up to Kubernetes clusters managing global traffic. So I want to leave you with this question for your own codebase. How would your current architecture handle an instant 10x traffic spike? Are your app servers truly stateless? Understanding these fundamental blueprints is really the only way to turn theoretical design into a robust, scalable reality. Thanks for joining me for this explainer, and keep building.